Convolutional Neural Network-based Classification of Brain Tumors Images, an approach. Abstract brain tissue biopsy is performed by surgery, which is rarely performed before explicit brain surgery. Improving technology and machine learning can help radiologists in tumor screening without invasive measures. A machine learning algorithm that has achieved great results in image classification and fragmentation is the Convolutional Neural Network, CNN. We are introducing a new CNN model for brain cell division into healthy or malignant. The advanced network is simpler than the already trained networks that already exist, and has been tested on T1 images with comparatively weighted magnification. The best result of the 10-point cross-verification method was obtained by intelligent recording confirmation of additional data sets, and, in that case, the accuracy was 96.50%. With a good knowledge of overall performance and good performance speed, the new CNN architecture could be used as an effective tool to support decisions for radiologists in clinical trials. Keywords: brain tumor, image classification, CNN, deep learning. Introduction. Diagnosing brain tissues share certain features and challenges in treating tumors in the body, but they also present specific problems related to the unique features of the organ in which they live. It is important to weigh the tissues according to their severity. Although other types of tumors, for example, meningiomas and neurinomas, are less common, gliomas is the most common brain tissue present in all the stages. Surgical biopsies, especially when taken with stereo carefully, may miss the worst part of the tumor and therefore reduce the tumor detection. Separation is a necessary and important step in image analysis. It is the process of separating an image into different regions or preventing the sharing of common and similar properties, such as color, texture, contrast, brightness, borders, and gray level. Brain tumors detection involve the process of separating tumor tissues such as edema and dead cells from normal brain tissue using WM, GM, and CSF with the help of MR images or other imaging techniques 2A5. In fact, experts have offered a variety of methods to automatically detect brain tissue and catalog typing using MRI brain imaging from the time of scanning and transporting medical images to a computer. On the other hand, neural networks, NN, and support vector machine, SVM, are the most commonly used methods used over the past few years. A major problem in classifying MRI images by specific neural networks lies in the number of images in the database. In addition, MRI images are available on a variety of planes. So the option of using all the planes will expand the size of the database. Pre-processing is required before feeding the images to the neural network. One of the well-known advantage of use of convolutional neural networks, CNN, is that manual pre-processing and feature extraction is not required. The purpose of this study was to classify a given image into a healthy or malignant through CNN. In this paper, we present a new CNN model for brain image processing to healthy or malignant. Literature survey. In order to know the state-of-the-art methods in the related study, following are the gist of papers. Remen et al., 2020, have proposed a method to detect brain tumors and their classification. The selected features are verified by the feed-forward neural network for final isolation. The three BRATS data sets for 2015, 2017, and 2018 are used for research, validation, and achieve accuracy of 98.32, 96.97, and 92.67%, respectively. Thilakara Cret al., 2019, have worked on in-depth learning algorithm, kernel-based CNN, with MSVM introduction to identify tumor automatically and efficiently. Image segmentation is done using MSVM according with selected features. From an MRI scan, the tumor is isolated with the help of a kernel-based CNN-based method. The experimental results of the proposed method indicate that the method used may enable the brain tumor separation to reach approximately 84% accuracy in comparison with existing algorithms. Zhang M. et al., 2020, have developed a methodology for detecting brain metastasis through MRI images. A total of 361 patients from 121 patients are used to train and test with fast region-based network with a convolutional neural network, faster RCNN. 270 scans of 73 patients were used for training, 488 planes are used in 91 scans of 48 test patients. Examination of data captured in MRI brain showed 96% sensitivity and 20 false metastases by scans. The results showed 87.1% sensitivity and 0.24 false metastases per unit. Todoroki et al., 2019, have proposed a system for the detection of liver transplants with different sizes in multiphase CT images using CNN's multi-channel protocol essential for transplantation. Test results reveal that memory points and dice coefficient can be significantly improved, by reducing the number of false positives, and the proposed method are compared with existing methods. Latifji et al., 2019, have proposed a method using 65 cases with 40,300 MR images obtained from the BRATS 2015 database. The work includes 26 low-grade glioma, LGG, cases and 39 high-grade glioma, HGG, tumors. The proposed CNN model exceeds existing methods by obtaining an average accuracy of 98.77%. Vivanti et al., 2018, proposed a convolutional neural network, CNN, method for automatic liver detection. Test results on 222 tissues from 31 patients revealed a common fracture error of 17%, STD equals 11.2, for a distance of more than mm, STD equals 1.8, much better than the independent segment alone. Importantly, the durability of the approach is improved from 67% of CNN's global division to 100%. Wang et al., 2019, have worked on focal cortical dysplasia, FCD, related to cortical developmental disorders. FCD automation detection strategies are proposed using MR images. All cortical patches are extracted from each axial plane, and these patches are divided into FCD and non-FCD using a deep convolutional neural network, CNN, with 5 layers of precision. Program quality testing, 9 out of 10 FCD images were successfully detected, and 85% of non-FCD images were correctly identified. Kutlu et al., 2019, have proposed a method to differentiate liver and brain tumors using convolutional neural network, CNN. Test results show that the proposed method had higher performance than the other classifiers, such as the proximity K, KNN, and the vector support machine, SVM. Results show that a 99.1% accuracy rate is obtained with a liver tumor classification, and accuracy rate of 98.6% is achieved in the brain tumor phase. From the literature survey, we can conclude that ample amount of work is carried in classification of brain tumor images. But only few researchers have reported their work using CNN. Hence, the proposed work is taken. Methodology. The proposed methodology consists of the following blocks as shown in Fig. 1. The work carried is discussed in detail through the following sections. Morphological operation. Magnetic resonance images from the database were of different sizes and were provided in INT16 format. These images represent the input layer of the network, so they were normalized and resized to 256 AA 256 pixels. In order to augment the dataset, we transformed each image in 2 ways. The first transformation was image rotation by 90 degrees. The second transformation was flipping images vertically. In this way, we augmented our dataset 3 times, resulting in 1,700 images. Gaussian blur. The Gaussian smoothing operator is a 2D convolution operator that is used to blur images and remove detail and noise. In this sense it is similar to the mean filter, but it uses a different kernel that represents the shape of a Gaussian, bell-shaped, hump. This kernel has some special properties which are detailed below. The erosion of a binary image F by a structuring element S, denoted Fs, produces a new binary image G equals Fs with ones in all locations, x, y, of a structuring element's origin at which that structuring element S fits the input image F, i.e. G, x, y, equals 1 is S fits F and 0 otherwise, repeating for all pixel coordinates, x, y. Erosion removes small-scale details from a binary image but simultaneously reduces the size of regions of interest, too. By subtracting the eroded image from the original image, boundaries of each region can be found, B equals F, Fs, where F is an image of the regions, S is a 3A3 structuring element, and B is an image of the region boundaries. The dilation of an image F by a structuring element S, denoted Fs, produces a new binary image G equals Fs with ones in all locations, x, y, of a structuring element's origin at which that structuring element S hits the input image F, i.e. G, x, y, equals 1 if S hits F and 0 otherwise, repeating for all pixel coordinates, x, y. Dilation has the opposite effect to erosion. It adds a layer of pixels to both the inner and outer boundaries of regions. Erosion with small, e.g. 2A, 2A, 5A, 5, square structuring elements shrinks an image by stripping away a layer of pixels from both the inner and outer boundaries of regions. The holes and gaps between different regions become larger, and small details are eliminated. Larger structuring elements have a more pronounced effect, the result of erosion with a large structuring element being similar to the result obtained by iterated erosion using a smaller structuring element of the same shape. If S1 and S2 are a pair of structuring elements identical in shape, with S2 twice the size of S1, then the holes enclosed by a single region and gaps between different regions become smaller, and small intrusions into boundaries of a region are filled in. Results of dilation or erosion are influenced both by the size and shape of a structuring element. Dilation and erosion are dual operations in that they have opposite effects. Let Fc denote the complement of an image F, i.e., the image produced by replacing 1 with 0 and vice versa. Formally, the duality is written as Fs equals Fc srot, 4. Where srot is the structuring element S rotated by 1800. If a structuring element is symmetrical with respect to rotation, then srot does not differ from S. If a binary image is considered to be a collection of connected regions of pixels set to 1 on a background of pixels set to 0, then erosion is the fitting of a structuring element to these regions and dilation is the fitting of a structuring element, rotated if necessary, into the background, followed by inversion of the result. Contour detection. Active contour is a type of segmentation technique which can be defined as use of energy forces and constraints for segregation of the pixels of interest from the image for further processing and analysis. Active contour described as active model for the process of segmentation. Contours are boundaries designed for the area of interest required in an image. The main application of active contours in image processing is to define smooth shape in the image and forms closed contour for the region. Active contour models involve snake model, gradient vector flow snake model, balloon model and geometric or geodesic contours. Curvature of the models is determined with various contour algorithms using external and internal forces applied. Energy functional is always associated with the curve defined in the image. External energy is defined as the combination of forces due to the image which is specifically used to control the positioning of the contour onto the image, and internal energy, to control the deformable changes. For the set of points in an image, the contour can be defined based on forces and constraints in the regions of the image. Different types of active contour models are used in various medical applications, especially for the separation of required regions from the various medical images. For example, a slice of brain CT image is considered for segmentation using active contour models. The contour of the image defines the layers of the region in the brain which is shown in the Fig 9. Active contours can also be used for segmentation of 3D images derived from different medical imaging modalities. 2D slices of image data are used for the separation of target object from the 3D images. These 2D slices of images in all directions along with the segmented target region are subjected to 3D reconstruction to segregate the regions. Mesh model of the 3D image is designed before applying active contour model. The mesh helps in the formation of deformable contours of the target object in the directional 2D slices of the 3D images. 14. Image augmentation. It creates training images through different ways of processing or combination of multiple processing, such as random rotation, shifts, shear, and flips, etc. Image data generator. An augmented image generator can be easily created using Image Data Generator API in Keras. Image Data Generator generates batches of image data with real-time data augmentation. The most basic codes to create and configure Image Data Generator and train deep neural network with augmented images are as follows. We can experiment with the following code to create augmented images with the desired properties. In our case, the following data generator generates a batch of 9 augmented images with rotation by 30 degrees and horizontal shift by 0.5. DataGen equals image data generator, rotation underscore range equals 30, horizontal underscore flip equals 0.5. CNN model. The network architecture consists of input, 2 main blocks, classification block, and output, as shown in figure 2. The first main block, Block A, consists of a convolutional layer which as an output gives an image 2 times smaller than the provided input. The convolutional layer is followed by the rectified linear unit, ReLU, activation layer and the dropout layer. In this block, there is also the max pooling layer which gives an output 2 times. Conclusions. We conclude that the proposed CNN architecture classifies given brain images into healthy or malignant. The developed network is simpler than already existing pre-trained networks, and it was tested on T1 weighted contrast enhanced magnetic resonance images. The best result for the tenfold cross-validation method was obtained for the record-wise cross-validation for the augmented data set, and, in that case, the accuracy was 96.50%.